Okay, so today we are going to discuss about angular velocity and its relation with linear velocity. Let's say we have a body. This is a three-dimensional body, and this body is rotating. This is pure rotation, rotating about this. Let's say this is z-axis. So this is y-axis and this is x-axis, and this is rotation. So if we point out a particle from this rotating body, this particle will revolve around this z-axis on a circular path, and this z-axis is passing through the center of this circle. And if we take this circle is lying in xy plane. It is parallel to xy plane. So let me bring it out here. And this is the circular path, and this is particle, and this circular path is in xy plane, and this is, let's say, particle, and I'm denoting it with P, and here we have center, and this is the axis of rotation, and we are saying that this is a pure rotation. That is, this body is not translating anywhere. It is just being rotated about this axis only. So if it rotates in such a way that this particle is moving on a circular path this way. So the rotation is like this. Now, this particle, let's say this particle was initially here. I am taking a part of its motion. So initially this particle was here, and after time t, delta t, let's say, after time delta t, this particle comes to a new position here. So it has traversed some angular displacement. Let's say this angular displacement is delta theta. So there will be angular velocity also, and this angular velocity is, if we are saying on average, this angular velocity is delta theta by delta t, and we denote this angular velocity with omega. So we can write here omega, and as this is a kind of vector thing, angular velocity, and this is kind of vector thing, we should also determine what is its direction. So if this is rotating, this body is rotating, and this particle is moving on this circular path, you can say in xy plane, if you are observing this particle's motion, in this xy plane, if you are observing this particle's motion, it is from top, from this side, it is anti-clockwise. So using right hand rule, you can say if we are curling the four fingers about this motion, so the thumb will indicate this direction. So the angular velocity is in this direction. Now, this is a kind of average. If we take limit for this time interval tending to 0, means we are going to find out now instantaneous angular velocity. So this will be delta theta by delta t. I'm just not writing this vector sign now. And then we used to denote this thing as d theta by dt. And this is omega. Let me write it here, average. So this is instantaneous angular velocity. Now, we want to know what is the relation between this angular velocity and linear velocity. So let me draw it again here. There is a motion on a circular path, and let's say this is center, and if this is radius, so radius is r, and this is angular displacement delta theta, and this is time taken, and let's say at any point, let's say the velocity is this one, linear velocity, and this is the direction, this is the axis about which this circular motion is taking place, and this is omega, and angular velocity here it is indicating towards positive z direction. Now if we take this small angle approximation, if you can remember this thing, we know that if this is theta this is L, and this is R radius. If you remember, for very small angle theta, we can write theta equals to L by R. So now we want to know that what is the relation between this linear velocity, initially magnitude, because we know its direction, it is always tangential at any point on this circle. So what is d theta now? So d theta can be written as d L by R by dt, and you can write it. Okay, let me move it little upward. So you can write it 1 by R, then dl by dt, and we know this thing d theta by dt, which has been written as dl by r dt. This is instantaneous angular velocity, so we can write it as this. And now I have taken this 1 by r outside from the differentiation because this is constant. On this particular circular track, this r is not going to change. Then we can write it 1 by r, and we know dl by dt is linear instantaneous velocity. So finally we can write omega equals to 1 by r into v, and we can write omega times r equals to v. Now we are getting here omega times r equals to v. Here omega is angular velocity, which is a vector quantity. R is also a vector quantity, it is kind of position vector, and v is linear velocity, which is also a vector quantity. So we are getting the product of two vector quantities as a result another vector quantity. So there should be cross product between these two things, and then cross product can be omega times r, or it can be r times omega, r cross omega or omega cross r. So let me check which one is compatible with this direction using right-handed system. So bringing back this diagram here once again, look, in this case, this is z-axis, this is y-axis, and this is x-axis. So the unit vectors along these three we can write as I cap, j cap, and k cap. So I cap, j cap, and k cap. Now we have to check in this particular scene if we are taking here origin. So the position vector is along positive y, which is along j cap. So unit vector along this position vector is j cap. So let's say its magnitude is r. So we can write position vector r as r j cap. Now omega is along positive z direction here. So if we want to write this vector omega, we can write omega, which is magnitude times k cap, and velocity vector, linear velocity vector is along, look, this is in xy plane, and this v is directly indicating inwards here. It is not upward actually. In xy plane it is along negative negative x-axis, towards the negative x-axis. So its unit vector along this velocity is like this here. In this way this velocity is indicating. So this is minus I cap, so we can write v times minus I cap. Now we have to check whether r cross omega or omega cross r is going to give us minus I cap. So whether j cap cross k cap, we know j cap cross k cap is giving us I cap, and k cap cross j cap, we have discussed these things already. So this is going to give us proper agreement with the vectors or unit vectors of these three vectors. So we have to check which one is correct here, means which one is compatible. So finally we can write this one omega cross r, and this is going to give us the direction to velocity vector. So this is omega cross r equals to velocity. So we have obtained the relation between linear velocity and angular velocity. This is not going to give us the appropriate result. Now here we have taken this origin at the center of this circle, but this may not be always the case, because look at this point. if we are choosing this to be origin. Okay, if we are choosing here origin, still we will have some other particles here in this system for which this center for the circular track is not the origin. So let me generalize the situation. Means when the origin is not at the center of this circular path, in that case we can obtain a very general scenario here, and I am going to do that. These things always hold. So if we are taking in general scenario here, let's say this is z-axis, this is y-axis, and this is x-axis, and this particle is revolving around this z-axis on this path, and here. Now the position vector is not being determined taking this one as origin, rather our origin is here. So if this is position vector, let's say particle is at this point, this is position vector r, and this is omega, and the particle is moving on this circular path as like so. This is point P, and this is so. If this position vector is making an angle theta with this omega vector, and let me write it. We know that we can parallelly shift vectors without changing their without rotating them or without changing their magnitude. These vectors will remain the same. So this is omega vector and this is position vector. And if this angle is theta, means here position vector and omega, these two things are at angle of theta. So this length is here now r sine theta. This length is now r sine theta, or this is kind of perpendicular component of this position vector. So we can write here now omega cross r is the linear velocity, and omega times r times sine theta equals to v, and magnitude wise and direction we can obtain. So this is the thing we want to know in general case if origin is not coinciding with the center of this circular path, or we can say this is r perpendicular component of this position vector. This is r perpendicular, then, and this will be r horizontal here. This will be r horizontal, this length, or you can see here this length is r horizontal, and this will be r horizontal, this will be r cos theta. And you know, if we take the horizontal component of this vector, position vector, the horizontal component will be facing along the this angular velocity vector. So the angle between these two are 0. So ultimately omega cross this component is going to give us 0. So in this way, now what about angular acceleration? Angular acceleration is written as alpha. Let me move it ahead. Okay, so angular acceleration. So acceleration is nothing but rate of change of velocity. So if we go for instantaneous angular acceleration, we have to take time derivative of this omega, and then we will have angular acceleration, which we denote by alpha. So, okay, up to here for this video. Next time we are going to discuss about torque or moment of force and angular momentum and relation of torque with angular momentum.